Welcome back to the second series of my lecture. Already we have taken the problem in the previous discussion. We'll try to solve the same problem once again in this today's lecture. We have considered a beam of three span with the different loadings. The span AB is loaded with a span AB of span 8 meter and loaded with a 15 kilonewton load. And span BC is loaded with a point load at center with 150 kilonewton. Span CD is loaded with a load 10 kilonewton per meter square with a 8 meter span. And substituting all these values into the bending moment equations, fixed and bending moment equations, we are getting the values of fixed end moment. For AB it is minus 80 kilonewton per meter square. For BA it is plus 18 kilonewton per meter square. For BC it is minus 112.5 kilonewton. For CB it is plus minus minus it will become plus 112.5 kilonewton, and CD it is minus 53.33 kilonewton. For DC it will be plus 53.33 kilonewton. Okay, this we have calculated. Next, let us calculate the stiffness factor. As already we have defined, the stiffness factor is nothing but 4EI by L for various members. Since and A is fixed length, and the stiffness will be equal to 4EI by L, and the stiffness of second member will be KCD equal to 0.667 EI, KCD equal to 0.5, KCD equal to again 0.5. Substituting all these values in this more deflection factor already we have derived in the previous equations. Then from that, AB is zero stiffness because it is fixed and it doesn't have any stiffness factor, sorry, distribution factor. And DC will be 0.424, and BC equal to 0.516, CD equal to 0.5716, and DC equal to 0.4281, and DF equal to 1. These all were substituted. Again, friends, this table is prepared where all the values, unbalanced moment and stiffness distribution factors and various members and joints have been mentioned in this equation, in this table. And first will be a joint. There are four joints. A joint is a fixed end joint. B is a continuous joint, which is meeting with a BA member and BC member, and joint C is meeting with CD member, CB member and CD member, and joint D is CD member only because it is a end joint. Okay, distribution factor for end A distribution, because it is a fixed end, it whatever moment it goes to the support, that moment will be absorbed by the support because it is a fixed end. It doesn't have it won't remonces. Okay, and at joint B, which is meeting with the two members, BA distribution factor is 0.4284, and BC is 0.5716. Similarly, for joint C, CB equal to 0.5716 and CD equal to 0.4284. And at joint A, since it is a simply supported end, whatever moment it comes, that moment will be absorbed, moment will be acting there. Further, it won't get distributed. Okay. Next, friends, first cycle. Here, friends, joint D is simply supported. Simply supported moment what we have written is 53.33, and let us write other fixed end moments. 80 minus 80 plus 81 minus 112.5 plus 112.5 minus 53.33 minus 53.33. Again, friends, okay, this is the first cycle. These are the values we are going to get it. Whatever, first we'll have to calculate the unbalanced moment at each joint. The joint B, the unbalanced moment is 80, 8 plus 80 minus 1, 2.5. If you take the difference of these two, then that will be unbalanced moment. That unbalanced moment will have to distribute to these two members depends upon their distribution factor. Okay, once if you distribute that at BA member, we are getting it as 13.923, and for BC member, we are getting it as 18.577. Okay. Similarly, you come to joint C. Joint C, CB is moment is 112.5. CD is minus 553.33. You take the difference of these two, that will be unbalanced moment, which is acting at C joint. That we have to distribute depends upon its stiffness, or depends upon stiffness and distribution factor. Okay. For CB member, the distribution factor is 0.5716, and you multiply that this value to the unbalanced moment, we are going to get the distributed moment will be 33.82. Okay, and for CD member, we are getting it as minus 25.35. Both are minus because the resulting moment, unbalanced moment is resulting unbalanced moment is positive value. That positive is the unbalanced moment. Then when you apply a resisting moment, that should be in a the opposite order. Therefore, we'll have to take it as minus. Next, 53.33. That since it is a simply supported end, it doesn't have any, it won't support any moment. Therefore, that moment you have to balance it with whatever totally moment will be, we have to balance it. The actual moment is 53.33. The distribution moment will be minus 53.33. This is the first cycle. Then, friends, in the second cycle, what we have to do is we have to carry over. These moments will have to carry over, and we have to keep on distributing it once again. Okay. 13, 13.925, half of this will be 6.962 in the same sign convention, because you know that the carryover will be whatever moment we are applying, that carryover to the far end will be with the same sign that I have explained. We have already derived this. Next, 18.577, this carryover will be 9.289. That is the same sign plus if it is value moment is positive, then this also should be positive. Next, 33.82, this carryover will be minus 16.91, and 25.35, this carryover will be 12.35. Next, 53.33 carryover will be 26.69. Clear? With this movement, we have to go for distributing it. Now, what is the unbalanced movement at B? It is 16.97 minus. And this, if you distribute further with a distribution factor, then we are going to get it as 7.244 at BA member, and for BC it is 9.662. Next, at C joint, one side it is 9.289, the other side it is minus 26.67. Take the difference of these two, and the difference will be in terms of minus. If the difference is minus, then distribution value will be opposite to that, it will be in plus. Therefore, 26.67 minus 9.286, the difference, whatever difference we are getting, that difference will be multiplied by the distribution factor. We are going to get it as 9.935 at BC member, and CD member we are getting it as 7.446. Again, friend, Again, friends, that is 26.67, whatever unbalanced moment is there, that will be carried out to this number as 12.37. That is 12.35, whatever it is, that will have to nullify it because it is simply supported. This cycle will continue till these values will be emerges into equal. Okay. One here we have done 5 cycles. These 5 cycles, the final value will be almost very minimal value, that is 0.42402 minus 0.536 minus 1.187. Other side it is minus 0.897, and this will be minus 0.703. Okay. Next, friends, we'll have to sum up the other moments, whatever end moments are there. With this, we have to sum up all these moments. If you sum it up, then we'll be getting the final moment. We should ensure that whatever final moment we are getting at the end, that at each joint should be either side it should be equal and opposite. Means if one side is plus, another side should be minus, and magnitude should be equal, because the basic principle is equilibrium condition. When the joint is in equilibrium, the resultant resultant moment must be equal to zero. Okay. Whatever unbalanced moments are there, that we are distributed depends upon the distribution factor. Then these are the end moments you are going to get it. Okay, this here it is tabulated. Next, friends, you have to calculate the shear force. You have to split this beam into 3 different beams, apply the end moments, and apply the end reactions. And using equilibrium equations, we can able to calculate the shear force. Then once if you get the shear forces, then you draw the shear force diagram. That way I have shown it here. And similarly, you draw the bending moment diagram. This ends the problem. Okay, friends. With this, I'd like to conclude today's discussion. We'll see the next. We'll continue in the next class. Thank you, friends. Thank you.